The purpose of this lab is to study constant velocity motion using Newton's second law. Newton's second law states that the sum of the forces equals the change in momentum divided by the change in time. From this, we can derive the equation for a velocity, which states that the final velocity equals initial velocity plus F net divided by m times delta t. And from this, we can derive the position equation, position final equals position initial plus Vf delta t. And the Vf we use for this is from the equation above it. And using an iterative process with small increments of delta t, we can repeat these two equations over and over again to find the final position over a certain extended period of time. And so for this lab, we're going to study constant velocity. And when velocity is constant, that means the sum of the forces is zero. Zero net force does not mean that there are no forces acting on the system. It just means that the vectors of the forces added together sum to zero. And in this lab, we're observing motion that has an ideal net force of zero. And technically, there will be some effects of air resistance, but for this short distance, they should be minimal. The procedure for this lab is to record an object at constant velocity and track its movement through Tracker. We can use this data to graph a position versus time graph. And then using the initial velocity, we can create a code that will predict the velocity over the time, and then we can compare the two graphs, the one that was the actual position versus time and the modeled position versus time graph. I chose to use a soccer ball rolling across horizontally with the camera parallel to the direction of motion for my object in constant velocity. I chose a soccer ball because I felt that the effects of friction from the ground would be less on a soccer ball, and the effects of air resistance would be minimal on a soccer ball over this short period of time. So here's the video I took. Here's my video in Tracker. I set the beginning and end points so that the ball would be in frame, and I also set the beginning point after my foot was in contact so that a force was not applied during the recorded motion. Here is the video played. For every frame, I recorded the center of the ball so that I could create a position versus time graph, which is displayed here. As you can see, I set the axis so that my motion is in the negative direction. Here's the code I used to create a model for my object. To begin with, these first few lines are just to create a visual representation of the ball in motion. Ball.m is the mass of the ball. The position vector starts at 0. The velocity vector starts at negative 2.44 meters per second because this is the initial velocity recorded. The total time is 0.633 seconds because that's what was used in Tracker. The delta t, which is the step that is used for the process, is 0.01. Here are the two equations used that are repeated many times to create a position versus time graph. We have the velocity equation and the position equation, which are the same as the equations that are derived from Newton's second law. Now I'm going to run the program. The top bit is just a visual representation of what is happening. Down here is the position versus time graph that was modeled, and down here is all of the data from the model. Here are the two position versus time graphs. The one in orange is the one generated from the model, and the one in blue is the one brought in from Tracker. As you can see, they are pretty similar to each other, but the one in orange has less steep of a slope. This means that the initial velocity I used was actually a little too small, and that's why the position ends up being less in the end. In conclusion, we can see that the model using Newton's second law accurately predicted the motion as compared to the actual recorded motion.